Section 5.3, the Fundamental Theorem of Calculus. Now, this theorem is extremely powerful, and it establishes the relationship between differentiation and integration. And what's so special about it is that it will allow us to evaluate definite integrals, just like we've done in Section 5.2, without using Riemann sums. So if we're tired of those rectangles, this is the answer. The fundamental theorem is broken down into two parts. We're going to start off with part one. Part one gives us a relationship between integrals and antiderivatives. So the wording for fundamental theorem of calculus, part one, says that if f of x is a continuous function over the interval from a to b, and capital F of x, notice this is a lowercase f of x, this is a capital F of x. We're defining the capital F of x to be the integral from a to x. Notice that's new. We haven't dealt with integrals that have bounds that are variables. A is some number that comes from the interval a to b. X, however, is a variable. It's the variable for the function capital F. Okay, so capital F of x is the integral from a to x of little f with t plugged into it, integrated with respect to t. Now this is kind of a dummy variable. Typically, little f is a function of x, just like capital F is a function of x. But since x is appearing in the upper bound of our integral, we do not want to also have x inside of our integral. And so we just do a simple substitution and say that the function is now a function of t, and we're integrating with respect to t. So if capital F is this integral, the fundamental theorem of calculus, we're going to call that FTC. Then FTC part 1 says the derivative of that antiderivative function capital F should give us back the original function little f with x as the variable again. So this is going to guarantee that every continuous function has an antiderivative. So that's what's pretty cool about FTC part 1. For sake of time, we're going to skip the proof, but I do encourage you to read it. It's on page 553. It starts off with taking the derivative of capital F of x, that antiderivative function, using the limit definition of a derivative, and then replacing it with the definition of f, and then simplifying that through just using the rules that we've learned throughout the semester. So take a look at it, have fun. Let's go ahead and start off with example 517. It's finding a derivative with FTC. Now, this is going to be so quick and simple that it's going to feel like nothing even happened. But the goal here is to look at this function, g of x. It's defined as this integral from 1 to x of the function 1 over t cubed plus 1 dt. FTC part 1 says if you take the derivative of that g of x function, it's the same thing as taking the derivative of the integral that's defining that g of x function. Oops. When you take the derivative of an integral and the variable that you're deriving with respect to is that upper bound, you can think of it as it just hops down into the function and falls into place. So the result is going to be 1 over x cubed plus 1, and we're done. So g prime is 1 over x cubed plus 1. And that's what the FTC says. So when you take the derivative of an integral where the upper bound of the integral is the variable that you're taking the derivative with respect to, you just simply copy the function over, replace the old variable with the new one, and drop the integration symbol. Example 5.18 uses FTC with the chain rule to calculate a derivative. So this time our antiderivative function, capital F, is the integral from 1 to the square root of x of sine t dt. Now this is a slightly different version of the last problem because our upper bound, although it is a variable, it's actually a function. And so what we need to do is use kind of a little substitution to simplify this so that it looks like a regular variable. The solution to this is to use a u substitution. So we are going to create a variable u that replaces that square root x function. And this is going to allow us to rewrite our definition for capital F as the integral from 1 to u of sine t dt. And when we take the derivative here with respect to u, or with respect to x, and u is involved inside of that, so we'll take the derivative of both sides here. If we're trying to take the derivative with respect to x of this integral that doesn't have a single x showing up inside of it, we have to think back to the fact that u is hiding a function of x inside of it, which means we're going to need to do a chain rule. We'll first take the derivative of the what's inside of the square brackets with respect to u, and then we will multiply by dx. Sorry, du dx. So we'll use the Fundamental Theorem of Calculus Part 1 on the derivative of the integral with respect to u, because it matches that definition, except for we're not using x, we're using u. So that would become sine u, and then times du dx. And now we're going to go back and replace u with x. So instead of sine u, it becomes sine root x. And then instead of du dx, we're going to actually calculate du dx. We're going to take the derivative of the u function, which we said was square root of x. We know that turns into 1/2 x to the negative 1/2. In other words, negative 1 over 2 root x. So our final answer would look like negative sine root x over 2 root x. Example 5.19 shows us how to use the fundamental theorem of calculus when we have two variable limits. So this time, capital F, the antiderivative function, is defined as the integral from x to 2x. So we have x's on both sides of our integral here, and we're integrating t cubed dt. The goal of this example is to find the derivative of that antiderivative function. Because there's variables on both limits of integration, we need to separate the integral into two parts. So we are going to start by inserting a separate point like 0. So we're going to write our lower limit all the way up to 0. And then we're going to start our second integral from 0 all the way up to our upper limit. There is a theorem that was covered in one of the previous sections that says you can flip the bounds on your integral if you multiply by a negative sign. So we're going to replace that first integral with negative integral from 0 to x. So notice I've swapped the bounds. and I've included a negative on that integral, still t cubed dt. And the only reason why we're doing that is so that it fits perfectly with the FTC part 1. So all we did was rewrite our antiderivative function as two separate integrals, both of them with the bottom bound being at 0, top bound being at x. Now we can take the derivative to finish the problem. So remember, we're trying to find the derivative of the capital F function. So we'll take the derivative with respect to x of each of our integrals. That first integral is already set up for the FTC part 1, taking the derivative with respect to x, and x is the variable that appears on the top bound. So we can simply just rewrite this as negative x cubed. The second integral, however, that requires a little u substitution because the top bound is actually a function of x. So let's let u be 2x. Then we're going to rewrite that integral as the derivative with respect to x of 0 to u t cubed dt. In order to take the integral with respect to x, we have to do the chain rule. So we'll first take the derivative with respect to u, 0 to u t cubed dt times du dx. And now this is set up for us to be able to use the Fundamental Theorem of Calculus part 1 on the integral portion. So that would become negative x cubed plus u cubed times du dx. Now remember, u we said was equal to 2x, so du dx would just be 2. So we'll multiply by 2 there. And we need to replace u with its terms of x, so that looks like negative x cubed plus 2x cubed times 2. If we have 2 cubed, that's 8. 8 times 2 is 16. That term looks like 16x cubed, so we've got negative x cubed plus 16x cubed, and that simplifies to 15x cubed.